Welcome to our talk. The title of the talk is A New LES Approach to Transcritical Mixing and Combustion Processes in High-Pressure Liquid-Injectant Engines. This is the content of our talk. First, we would like to talk about what was found from our review, and then we go to analysis of possible subgrid scale thermodynamic and fluid dynamic instabilities in transcritical mixing. And then we'll go to proposed subgrid scale model functioning at pseudo-boiling surface in two-phase flow LES. And then, lastly, we would like to show a demonstrative example. Flame stabilization mechanism has been extensively studied for various combustors. Its fundamental concepts derived for low-pressure combustors are useful for high-pressure combustors as well. For liquid rocket engines, Candle's group examined the flame structure anchored behind a LOX post. This is a figure obtained in the experiments conducted about 20 years ago, showing a combined OH star emission and backlighting images. A diffusion flame surrounds the cryogenic oxygen jet. This enlargement of an immediate vicinity of the LOX post indicates that the flame base is almost attached to the post. An LES reproducing the flame anchoring at the LOX post was conducted by Yang's group. This is a calculation result for LOX methane shear coaxial injector. Since the LOX post end portion is vacuumed to balance with the net shearing forces acting from the outer gas stream and the inner liquid stream, a reverse flow is generated behind the LOX post. The diffusion flame extending from the anchored flame tip is located within the reverse flow of high temperature fluid as shown in this figure. The reverse flow region coincides with the high temperature and water vapor concentration regions. Therefore, the global combustion feature read from this figure is that the heated O2 and CH4 increase their diffusivity and maintain the diffusion flame moving upstream, and the combustion products diffuses into the O2 and CH4 streams at upstream locations. Now, there are LESs which simulate the whole combustion system. Small kinematic viscosity at high pressure enables the coaxial injector elements to establish wake flows behind the thin LOX posts. Such a situation is similar to that of diesel engines and gas turbines. More fundamentally, a single cryogenic liquid jet injected into a quiescent supercritical gas was investigated for decades to explore the transcritical mixing characteristics. In the next two slides, we will see two kinds of experimental evidence from 1. Air Force Research Laboratory and 2. German Aerospace Center. This slide shows the shadow graphs of a jet of liquid nitrogen at an initial temperature about 100 K into room temperature gas nitrogen at supercritical pressures. Although the overall feature appears similar to the subcritical case, there are significant differences due to the absence of phase separation. Figure A clearly shows that the formation of comb-like structure of dense fluid resolving into the surrounding light fluid in the mixing layer. This feature has been considered to be characteristic to the transcritical mixing. Now we have a question: what are these? Because no explanation has been provided of these portions enclosed by the two red circles, although the same pictures are published in many journals. We will try to explain them at the end of this talk based on our simulation result to explain what supposedly happened in this experiment. Figure A shows the density distributions along the jet center line from the injector exit, which was derived from Raman spectroscopy measurements. The inset shows the measured chamber pressure, jet velocity, as well as the measured liquid nitrogen temperatures at the nozzle entrance and exit in each experiment. All cases reduced to an asymptotic curve downstream of x over d larger than 20, where mixing occurs according to the classical entrainment theory. This suggests that the phenomena intrinsic to real gas effect strongly emerges in the vicinity of the injector. It is notable that the near-injector behavior is significantly different depending on the injector entrance and end temperatures. It suggests that there's a certain temperature between 120 K and 130 K at which the supercritical fluid behavior changes from a liquid-like to gas-like one. Such a phenomenon occurring for a supercritical fluid heated by the tube wall was first found in a heat transfer study of Kafengos and Fedorov and named pseudoboiling, or PB, for its resemblance to the subcritical boiling phenomenon. Figure B shows Banuti and Hahnemann's model explaining the actual density profile changes in Figure A in terms of the PB concept caused by the tube wall heat transfer and subsequent Kelvin-Helmholtz instability Topical mixing. Many earlier simulations of a single cryogenic liquid jet issued into a quiescent supercritical gas were conducted during this decade. They cite the finger-like entity formation as a characteristic feature of transcritical mixing. However, there are no simulations which succeeded in reproducing the finger-like entity formation even when the used minimum grid size was shorter than the finger diameter. What was mainly reported is the agreement of calculated central line density distribution with certain experimental measured ones. The followings are what we found from our review and our proposal to resolve the identified problems. Consider a mixing layer developing on the surface of an injected cryogenic nitrogen jet into a room temperature hydrogen gas. This figure shows the phase diagram representing the possible thermodynamic states for the mixing layer. Large X denotes the mole fraction of hydrogen, whose critical value changes depending on the temperature and pressure, and we obtain the critical trajectory line connecting the critical points of nitrogen and hydrogen, denoted by this red line. Above this line, the mixture is in a supercritical state. The supercritical fluid behaves like a liquid on the left-hand side of the Widom line and like a gas on the right-hand side. Below the critical trajectory, the mixture is in a two-phase state and the injected liquid has its surface. This blue line represents the range treated by a typical LES in the literature. The system pressure is 4 megapascal, a little higher than the critical pressure of nitrogen. The injected liquid temperature is about 110 K, lower than the critical temperature of nitrogen. Since the calculated mixture state should cover all thermodynamic states on the blue line, the injected liquid must have a surface at an early stage of the LES. However, all LES found in the literature have only solved the governing equations stemming as a supercritical mixture. Almost all of them have claimed that the calculated results characterize the transcritical mixing. In our understanding, we follow the usual terminology, transcritical, meaning that passes through a critical state, namely between subcritical and supercritical states. In this respect, there is no LES solving the transcritical mixing layer. Therefore, we started a manuscript in our attempt to give an answer to why such a thing happened, by citing Umemura's old paper on high-pressure droplet evaporation and combustion problem. All numerical simulations of droplet evaporation combustion failed when the droplet surface state approached the critical point. Umemura examined why more than two decades ago. This slide illustrates the findings. Eliminating the coordinate r from the instantaneous temperature T and fuel mass fraction y, we can express y as a function of T, which changes with time like this. The y value jumps at the droplet surface. As the surface temperature rises, the gap is reduced and vanishes when the surface reaches the critical state. In this case, the y-curve must take the form illustrated in this figure, indicated that dy dt should diverge at the critical point so that the subcritical evaporation regime might change to the supercritical evaporation regime continuously. Defining the heat flux large phi as this, the fuel mass flux is expressed as J, like this. Physically, the diffusive mass flux across the critical surface J should be finite. This condition is satisfied only when the effective diffusion coefficient D vanishes at the chemically critical surface. Simple use of kinetic theories D12 as D does not satisfy this condition. It causes a divergence of J at the critical surface, and the simulation fails at the instant of transition. Einstein's mutual diffusion coefficient, defined like this, satisfied the required condition because phi becomes 0 at the critical point and phi equals 1 at the thermodynamically stable state apart from the critical state. The governing equations of current LES are the fluid dynamic differential equations supplemented with the van der Waals type equation of state and physical properties correlation equations. The physical properties are a function of thermodynamic variables used in the equation of state. Therefore, application of the equation of state to each point in the flow field solved by LES means that each fluid particle described by LES must be in a locally thermodynamic equilibrium state. In other words, as far as the van der Waals type equation of state is applied to each fluid particle state description, the arguments made for DNS in the previous slide should also hold for the current LES. However, the evaluation of eddy diffusion coefficient used in the current LES is the Smagorinsky eddy viscosity divided by a constant Schmidt number, which does not satisfy the vanishing diffusivity at the LES resolved critical surface. The eddy diffusion coefficient also must be multiplied by the thermodynamic correction factor phi, as shown in the previous slide. Strictly speaking, this is why the current LES cannot treat the transcritical mixing process. In fact, LES is advantageous in the use of large grid widths. Let us consider the concentration change calculated at two neighboring grid points in the current LES. The two solid circles in this figure are the concentration values YA and YB evaluated at some instant. At the next time step, these concentration values changes by an amount corresponding to the time step lengths. The same calculation proceeds even when there is a thermodynamically unstable layer exists between the two grid points. In reality, the following should happen in this case. Using a diffusion coefficient d modified by phi, we consider the microscopic concentration field evolution governed by this diffusion equation. Then, the concentration distribution changes as shown by red lines in a very short period, like this, and phase separation takes place. This is the reason why current LES, which only used unmodified diffusion coefficient, could not describe the phase separation even using a very fine grid system. Therefore, to describe the transcritical mixing state, we have to multiply the eddy diffusivity by the thermodynamic correction factor phi as well. Now we'll talk about pseudoboiling point, PB. PB is an important property which characterizes transcritical phenomena for supercritical fluid in a thermodynamically stable state. We found out two possible subgrid scale instabilities associated with PB, which will be explained in the subsequent slides. The PB point is well defined for a pure substance, as exemplified in figure 6 here. The volume expansion rate dV dt, thereby specific isobaric heat capacity Cp, has a significant peak at certain temperature depending on pressure. Thus, the PB temperature Tb is an indicator of the crossover between liquid-like and gas-like supercritical fluid. To understand thermohydrodynamic behavior in the vicinity of the PB point, we first consider a 1D problem, the nitrogen which occupies a semi-infinite space with a uniform temperature 300 K in the right-hand side, like this, and temperature 105 K in the left-hand side, are contacted at time t equals 0. It was assumed that the thermodynamic pressure P is always constant at 4 megapascal over the whole region. Figure 7 shows the instantaneous temperature T, density ρ, and velocity U distributions. Since the overall fluid is cooled, a hot gas flow toward the cold fluid is induced. The volume expansion produces the velocity U toward the hot fluid, which peaks near the PB temperature of 130 K. It is found that compared to the temperature, the density changes rapidly near the PB location. This suggests that for a large LES grid width, schematically shown here, the effects of SDS large density difference across the PB location must be taken into account using an Sds model. Since the PB location is initially at NB equals 0, it is found that NB moves toward the hot fluid side, and the velocity difference across the PB location does not take a large positive value. This is because the hot fluid is cooled. It is important to note that this property should be shared by the shear layer of figure 1 on slide 5. Therefore, it is found that the PB location would hardly reach the jet center line without the growth of KH vortices. This case corresponds to cases 3 and 7 in case 2 of slide number 6, and the center line density keeps a large constant value until the arrival of PB location. Consider a case when a cryogenic fluid is heated up and the PB surface moves toward the cooler side, accompanying the significant jumps of velocity and density across the PB surface. The PB surface will become hydrodynamically unstable due to Landau instability. This instability may produce dense fluid spikes extending into the light fluid region. However, the invisible growth rate expression derived by Landau is not useful because it predicts an infinitely large wave number of dominant dense fluid spikes. We understood the physical reason why a finite valued wave number maximizing the growth rate has not been derived, and we succeeded in resolving this difficulty as detailed in supplementary material. Very interestingly, it was found that only the transcritical condition can manifest this instability in a short time. The most unstable wave number, which can be determined by taking a viscous effect into account, is given by this. We estimated the wavelengths of dense fluid threads produced by the hydrodynamic instability at the PB location. It could take a value of order of 10 micrometers for the experimental condition of figure 1 on slide number 5, consistent with the spacing of orderly dense fluid threads observed in this figure. However, as explained later, almost the same wavelengths of comb-like dense fluid structure can be formed by the Rayleigh-Taylor instability at the PB surface downstream of the injector. A similar thing can be considered for a binary component system. But, as mentioned previously, the mass fraction Y of condensable component in the mixing layer depends on the mixing process and should be locally treated as a function of temperature T. Therefore, the realizable PB location must be determined by the earliest calculation process of the mixing layer itself. This can be done by using these two equations. Equation number 1, heat and mass conservation across the PB surface, and number 2 is a characterization of TBY. The formation of KH vortex train along the injected cryogenic liquid is apparent from this LES result by Yang's group, who made the calculations corresponding to the experimental conditions of figure 1 of slide number 5. The passage of a KH vortex train periodically vibrates the PB surface transversely. Therefore, Rayleigh-Taylor instability would be excited and the dense fluid spikes would extend into the light fluid. The classical inviscid linear stability analysis predicts the growth rate, which is not acceptable because an infinitely short wavelength dominates. The viscosity tends to suppress the short wavelength deformation. The frequently cited dispersion relation for miscible dense and light fluids is found in Chandrasekhar's book, for example. Unfortunately, this is not acceptable either because the maximum growth rate at k equals 0 is unphysical. We found that this discrepancy comes from the application of shear stress balance at the interface, which deforms in a sinusoidal shape according to the normal mode function used in the conventional linear stability analysis. To make the mode function effect more realistic, we replace the shear stress balance condition with the vanishing tangential velocity condition at the PB surface and obtain this dispersion relation, which yields the maximum growth rate, that's this, at the finite wave number of this. This result is interesting in that the small kinematic viscosity at the PB location could result in a considerably short wavelength spike formation, which is comparable to the wavelengths of the experimentally observed comb-like structure. In addition, the magnitude of acceleration g in a supercritical fluid jet is anticipated to take a larger value than that in a subcritical fluid jet. Therefore, we developed the Sds model, which describes the dense fluid spike formation from the LES-resolved PB surface. To do so, we need additional analysis and consideration about the nonlinear instability characteristics of 3D version Rayleigh transfer instability for tempospatially sinusoidally varying acceleration g of PB surface, which are detailed in supplementary materials. Please read the supplementary material if you are interested in them. The important point is that the Sds model could generate the Sds comb-like dense fluid structure for sinusoidally varying acceleration as illustrated in this figure, like this. The influence of shear rate on RT instability was analyzed here. It indicates that the large shear rate suppresses the long wave RT instability. The wave number of RT instability must satisfy this inequality shown here. This is a balanced calculation result comparing DNS and LES. Only KH instability is captured similarly to Young's calculation, which corresponds to figure 1 on slide number 5. It is said that Smagorinsky Sds model is a poor model because of this discrepancy, but we think that it's a natural calculation result for this reason. Therefore, the integration of a Sds RT instability model is indispensable in LES. The Sds model operating at the pseudo-boiling surface can be integrated into two-phase flow LES by replacing our previously developed turbulent atomization Sds model operating at the liquid surface. The local interface is governed by this, and interfacial conservation conditions are shown here. The shape and the thermodynamic state of the local pseudo-interface changes tempospatially because the dense fluid spike formation changes the subsequent light fluid LES flow field evolution, and thereby the pseudo-interface behavior itself as well. Every inertial dense fluid element of each spike tends to keep its initial velocity gained at the instantaneous bubble tip location. The spike behaves as a free jet into the light fluid region and may play an important role in the transcritical mixing process. When such RT instability occurs, the subsequent flow evolution changes from the case where the instability is not captured. Therefore, a desirable LES should be the one which could capture this possibility and predict two-way interactive evolution of flow. This slide illustrates how the proposed two-phase flow LES could cover all transcritical mixing processes. Again, the shape and thermodynamic state of the local pseudo-interface changes tempospatially because the dense fluid spike formation changes the subsequent light fluid LES flow field evolution, and the pseudo-interface behavior itself as well. Such a pseudo-interface exists as a continuous surface in space until the interface temperature increases to a certain value and the flow field becomes a completely superclit critical state, like this, or when the pseudo-interface location becomes thermodynamically unstable and phase separation takes place, like this in the subcritical regime. This slide shows an example. Without any tuning for experimental fitting, we conducted our LES to check the formation of Sds pseudospray, mimicking comb-like dense fluid threads, at the pseudo-interface for a single transcritical jet. Importantly, no disturbance was imposed at the injector exit. This injection condition roughly corresponds to that of figure 1 on slide number 5. This figure shows the time sequence of jet development with oxygen concentration contour on the center plane. The Sds Lagrangian particles pseudospray are also shown on the right-hand side, which demonstrates the formation of Sds comb-like dense fluid structure due to the RT instability at the PB surface. The instantaneous pseudo-interface profile on the center plane is indicated by a black or red solid line in each figure. The same large density gradient magnitude layer appears along this line, consistent with Young's calculation. The diffusion coefficient takes a small value at high pressure, therefore the binary mixing is dominated by a large area increase in the contact surface of the two species. In the present simulation, the contact surface consists of the pseudo-interface and the sum of Sds dense fluid thread surfaces. The meandering of dense fluid jet generates a large size of vortices and reduces the intact lengths significantly compared to the subcritical case. As a result, the contribution of pseudo-interface area increase is limited. The total surface area of the Sds dense fluid threads formed near the injector may take a much larger value than the pseudo-interface area. This implies that the dense fluid thread solving into the light fluid could be a main contributor in the mixing layer. In fact, the calculated instantaneous density distribution along the center line clearly shows this. Note that the oxygen concentration distribution is not asymmetric and steady. Unlike the pseudospray present within the intact lengths, the pseudospray present downstream of the intact length is produced from the upstream pseudo-interface at an early time. Each dense fluid thread solves into the light fluid and disappears after an elapse of time. This is why the pseudospray density is rarefied downstream. Seemingly, the pseudospray behavior in this region could correspond to the dense fluid thread structure observed in the experiment as shown in figure 1 of number 5. Finally, in conclusion, we can say that in reviewing the transcritical jet flow LES in the literature, a lot of questions were found. We analyzed the underlying physics to resolve them and developed a new LES scheme which addresses the truly transcritical mixing properties missing in the current LES. Thank you very much.